Hello, welcome to another module in this massive open online course. Alright. So, let us continue our discussion on the Fourier transform, correct. Let us now look at the properties of the Fourier transform. Let us look at the modulation property of the Fourier transform. Alright. So, let us look at the modulation, that is what happens to the Fourier transform of a signal which is modulated. Alright. So, this is the modulation property of the Fourier this is the modulation property of the Fourier transform. What do we mean by modulation? Modulation simply refers to the operation, that is x tilde t, which is x t multiplied by a complex, a sinusoid with a very high frequency, that is multiplied by a sinusoid at a very high frequency. In fact, this is one of the most fundamental principles of communication, that is, this is a complex sinusoid which is termed as the carrier, and this f c, that is this quantity f c, this is the carrier, this quantity f c is the carrier frequency. All right. So, we multiply by the sinusoid, this quantity f c, this denotes the carrier frequency, and x t is your signal, and x tilde t is termed as the modulated signal. This is termed as the modulated signal. This process is modulation. Now, in general, when we modulate it, of course, here we are employing a complex sinusoid. In general, we employ a real signal, that is either a cosine or a sine signal. All right, but in general, but in principle, this can be represented as x t multiplied by this complex sinusoid e raised to j 2 pi f c t. This complex sinusoid at the carrier frequency f c. Alright, e to the e raised to j 2 pi f c t is the complex carrier, f c is the complex frequency, f c is the carrier frequency, and this carrier frequency is much higher, that is in communication systems this carrier frequency is much higher, typically much higher than the maximum frequency, orders of magnitude higher than the maximum frequency of the, or maximum much higher than the bandwidth of this signal x t. Alright, and this process is termed as modulation. Of course, we are going to keep encountering this frequently, right, as we go through the various modules in this course. This principle of modulation in various communication systems, we are going to keep encountering this very frequently, and this is a very key aspect, a very important step in any communication system. All right. Now, what happens to the Fourier transform under modulation? That is, if I consider a signal x t which has Fourier transform, that is Fourier transform pair with, that is x t which has Fourier transform f f x f. Now, what is the Fourier transform of the modulated signal x tilde t? Well, x tilde f equals minus infinity to infinity. I can write this as x t or x tilde t e to the power of minus j 2 pi f t dt which is substituting the expression for x tilde t, that is x t e to the power of j 2 pi f c t e to the power of minus j 2 pi f t dt, which is equal to, now you can write this as x t e to the power of minus j 2 pi f minus f c dt, and now you can see this is nothing but the Fourier transform of x evaluated at the frequency f minus f c. So, what we have is we have this interesting result, we have x tilde f, the Fourier transform of the modulated signal is simply x of f minus f c. It is a very interesting result, and as I said, since modulation is a very important step or a very important aspect of any communication system, this principle is used very frequently. It is very important in communication. That is what we have seen is x tilde f is x f, that is x tilde f, the Fourier transform of the modulated signal is x of f minus f c. That is, it is simply a shifted version, that is the Fourier x f minus f c is the Fourier transform of x f shifted to f c, that is shifted by f c, correct. So, what we have is x tilde f, this is the Fourier transform this is simply the Fourier transform of x f of x f shifted by f c, that is. So, modulation in time. So, the principle is modulation in time. If you modulate modulation in time, this is equivalent to shift in frequency by f c, where f c we know is the carrier frequency. So, modulation in time. So, if we modulate the signal in time, that is simply that can be envisioned as take the original spectrum and shift it in the frequency domain by f c, where f c is the carrier frequency. And this is an important principle in communication systems, as I have already said. For instance, let us take a simple example to understand this in a practical communication system, correct. Let us consider a GSM communication system. As we all must be familiar, GSM is a wireless standard. It stands for the Global System for Mobile Communication, and in fact, it is one of the most popular wireless technologies or wireless standards, one of the most popular wireless technologies which is used by a large number of wireless cellular users. All right. So, GSM is the global for mobile, and it is a very dominant wireless and it is a dominant wireless technology. For instance, let us take a simple GSM. Let us GSM, if you look at the original signal, correct, the what is termed, it has a bandwidth of W equals 100 kilohertz centered at frequency 0. So, this is the original message spectrum or the original message this is the original message signal spectrum. Now, for the purpose of transmission, this is modulated to a very high carrier frequency. So, this is modulated by a very high carrier frequency. I am not drawing it according to scale, all right. So, it is modulated to a very high carrier frequency which is simply, so now it is shifted by Fc. So, this will be Fc minus W, Fc plus W. So, this is shifted to Fc. We have already seen Fc is the carrier frequency, and in GSM typically Fc equals either 900 megahertz or 1800 megahertz. So, what you are seeing here is that you have an original GSM signal, the message signal, which is of a bandwidth 100 kilohertz, centered at frequency 0, correct. Now, for the purpose of transmission, I have to employ a very high carrier frequency, or in GSM employs a very high carrier frequency, which is 900 megahertz or typically around 1800 megahertz, and therefore, this message spectrum is modulated with the carrier at 900 megahertz, which means the original spectrum, which is centered at 0, is shifted to the carrier frequency, that is at 900 megahertz or 1800 megahertz, depending on the carrier frequency. Now, the other thing that you can observe is the signal bandwidth is 100 kilohertz, right, which is of the order of 10 to the power of 3, correct, or 10 to the power of 5, 100 kilohertz, that is 100 into 10 to the power of 3, so 10 to the power of 5, but the carrier frequency is 900 megahertz, which is 900 into 10 to the power, or you can roughly say 1000 megahertz, 1000 megahertz is 1 gigahertz, that is 10 to the power of 9. So, your original message is of bandwidth 10 to the power, around 10 to the power of 5, and when you translate it, the transmitted symbol, that is a modulated signal, or the carrier has a frequency that is the order of 10 to the power of 9. So, you can see that the carrier frequency Fc is much larger than the message bandwidth, and this as a reason we are going to explain it in greater detail once we come to the modulation aspect, but you can see that the modulating frequency, the carrier frequency is much higher than the message bandwidth, and this is a very important principle in communication. So, you can see basically that Fc, so what you can see is that your Fc equals 900 megahertz is much larger than W, which is equal to 100 kilohertz, and this W is equal to the message bandwidth, and this is also termed as this original message signal is also termed as the baseband signal. This original signal is also termed as your baseband signal. This baseband signal, alright, is centered at 0 frequency, modulated to a very high carrier frequency and transmitted over the wireless radio channel. This is the principle of modulation. Modulation means basically transmitting, basically multiplying by a sinusoid of a very high carrier frequency for the purpose of transmission. Okay. Alright. So, this is an important principle of communication. Now, let us look at another very special function in both signal processing and communication, for which we want to compute the Fourier transform, and this is basically the unit impulse function. So, let us start looking at another very interesting and important function. Which is the unit impulse function. Now, this unit impulse function, this is also known as the Dirac this is also known as the Dirac delta function, denoted by delta t. This is the Greek symbol for delta, and this is represented in the time domain. Well, let us first define this. Delta t, this Dirac delta function, is defined as 0 for t, for all t not equal to 0, and it is 0, and for t equal to 0 it is not really defined. The delta function for t equal to 0, it is not really defined, not particularly defined. However, the integral minus infinity to infinity of delta t, this is equal to unity. That is, the area under this function, that is, if I look at this function, the area under this okay, the area under this Dirac delta function is always unity. That is, it is 0 everywhere. So, value at 0 is not defined. However, the area under this, that is integral from minus infinity to infinity delta t, that is basically unity, that is basically always a constant, that is 1, and it is represented as follows. This special function, this delta function, is represented as follows, that is, I have 0 everywhere, and at 0 it is represented using an impulse or a unit. This arrow, this line with arrow pointing upwards is known as an impulse. That is, it is 0 everywhere, and at 0 it has its magnet, its value is not defined. So, it is shown with an arrow which is pointing upwards, is also termed as an impulse, or as we said, the unit impulse function, typically also termed simply as an impulse. Its meaning is evident from the context. And the way to understand this impulse is, it cannot be described, it cannot be visualized intuitively. The way to understand this is basically think of a pulse, that is, the way to understand this special function which is the impulse is to think about a pulse which is of height t of width 1 over t. So, it spans 1 over 2 t minus 1 over 2 t to 1 over 2 t. So, width equals 1 over t. Alright. So, area of the pulse, let us denote this pulse by delta t of t, delta or sub capital T of t. Area Now, you can see the area for any capital T, the area of delta T T is basically its height, which is equal to the area is basically the height, which is equal to T into the width, which is 1 over T, which is equal to unity. So, we can think of a height impulse with height capital T, width 1 over T spanning from minus 1 over 2 T to 1 over 2 T. So, that the area is basically always capital T into 1 over T, which is basically 1, this is unity, all right. Now, as the limit T tends to 0, that now as the limit T tends to infinity, which means the height keeps increasing and the width keeps shrinking, yet the area under it is a constant. In the limit capital T tends to infinity, it becomes the unit impulse function. So, delta T can be understood as the limit. One way to understand delta T is the limit as T tends to infinity of delta T, which means, that is, this means the height tends to, height of the pulse tends to infinity, width tends to 0, however, area is 1, which is a constant. So, this is basically one way to sort of intuitively sort of visualize this unit impulse function, which otherwise is very difficult to visualize or understand intuitively, all right. Think of it as a pulse with width 1 over T, height capital T as the limit T tends to infinity, so that the width shrinks to 0, the height really becomes infinity, all right. And this impulse has several interesting properties, all right. So, let us look at, and it is important to understand these properties and it is important to use, and we are going to use this function very frequently to study or to define the various aspects and study the various properties of communication systems, all right. So, the impulse has several interesting properties, all right. For instance, for any function, any continuous function phi of t, for any continuous function phi of t, phi of t, for any continuous function phi of t, for any function phi of t continuous at 0, all right, need not be continuous in general, for any function phi of t continuous at 0, phi t delta t is equal to phi of 0 delta t, and this is natural since delta t is 0 only for t, delta t equal to 0 for any t not equal to, so delta t is 0 for any t not equal to 0. So, phi of t into delta t, when phi of t is continuous at 0, is simply phi of 0 times delta t. So, delta t is sort of picking the value of this function phi of t at t equal to 0. So, sort of picks, or we can put it over here, picks, or this operation picks, this picks value of phi of t at equal to 0. Picks value of phi of t at t equal to 0, that is phi of t at evaluated at t equal to 0. Now, naturally further integral minus t to minus infinity to infinity phi of t delta t by the above property is integral phi of 0 delta t dt. Phi of 0 is constant, so it comes out of the integral. So, this is nothing but phi of 0 integral minus infinity to infinity delta t dt, this is equal to phi of 0, all right. So, what we have is basically integral minus infinity to infinity phi of t dt equals phi of 0. Okay. So, that is for any function phi which is continuous at t equal to t equal to 0. Now, let us consider a shifted version of this impulse, that is shifted to t naught, that is delta t minus t naught. So, let us consider delta t minus t naught. Naturally, this is 0 if for every t not equal to t naught, correct. What is this? This is impulse shifted to t equal to t naught. Therefore, you have your axis, correct, your time axis, this is your time, and this denotes the impulse shifted to t naught, all right. So, this is basically your delta t minus t naught, all right. This is the time axis. This is your impulse shifted to t equals t naught. So, naturally, phi of t, again phi of t into delta t minus t naught, since delta t minus t naught is 0 for all t not equal to t naught. This is simply phi of t naught into delta t minus t naught, correct. So, this is obviously for any function phi of t continuous at t equal to t naught. Now, I have to qualify this statement. This is for any function phi of t continuous at t equal to t naught. Any function phi of t continuous at t equal to t naught. Further, if I integrate this, that is integral minus infinity to infinity phi of t delta t minus t naught dt, this is naturally integral of phi of t naught delta t minus t naught dt, which is phi of t naught. Okay. So, this basically picks the value or picks value of phi of t picks the value of phi of t, that is integral phi of t delta t minus t naught dt from minus infinity to infinity is basically phi of t naught. Already basically it picks the value of phi of t, the function phi of t at t equal to t naught. Now, provided phi of t is continuous at t equal to t naught, all right. So, this is an important constraint or the qualification of this argument or this result to keep in mind. Okay. All right. Now, let us look at the Fourier transform of this unit impulse, which is going to be very important. The Fourier transform Now, the Fourier transform of the unit impulse, that is easy to evaluate, that is your Fourier transform of delta t, this is equal to minus infinity to infinity delta t e power minus j 2 pi f t dt. All right, this is a standard expression for the Fourier transform. And now, you can treat this function phi of t, and by the property that we have shown before, that is integral minus infinity to infinity delta t phi of t dt is nothing but phi of t evaluated at t equal to 0. So, this becomes e power minus j 2 pi f t evaluated at t equal to 0, and e power minus j f 2 pi f t evaluated at t equal to 0 is 1. So, this is simply basically just 1 at all frequencies in the frequency domain, all right. And this is the Fourier transform of this function, which is the impulse. So, these two form a Fourier transform pair. So, delta t, the Fourier transform is simply one unity for minus infinity less than or equal to, that is for all frequency, minus infinity less than or equal to infinity. These form a Fourier transform. These form a Fourier transform pair. Again, similarly, you can find the Fourier transform of the shifted impulse delta t minus t naught, correct. The shifted impulse f t of delta t minus t naught equals minus infinity to infinity delta t minus t naught e power minus j 2 pi dt. Once again, this is your phi t from the previous properties. So, this is e to the power of minus j 2 pi f t evaluated at t equal to t naught, that is e to the power of minus j 2 pi f e to the power of minus j 2 pi f t naught. So, delta t minus t naught, delta t minus t naught, that is the shifted impulse, is basically the Fourier transform pair is delta t minus t naught is e to the power of minus j 2 pi f t naught. And notice that this is, well, of course, we know this is the shifted impulse, this is your shifted impulse, and this e to the power of minus j 2 pi f naught in the frequency. Remember, this is in the frequency domain, not the time domain. So, this is a complex sinusoid in the frequency domain. correct. Usually we have the sinusoid in the time domain, which is e power minus j 2 pi f naught t, which is frequency f naught, which is a function of time, correct, at frequency f naught. Now we have the analog in the frequency domain, e power minus j 2 pi f t naught, alright. So this is a complex sinusoid, correct, a complex sinusoid in the frequency domain. This is defined for all frequencies minus infinity less than or equal to f less than or equal to infinity. So this is a complex sinusoid in the complex sinusoid in the frequency domain. So the shifted impulse delta t minus t naught has basically the Fourier transform, which is a complex sinusoid in the frequency domain, alright. So basically let us stop this module here. We have looked at the modulation property, alright. The modulation is a very important, we said modulation is a very important step in any communication system, alright. And subsequently we looked at this very interesting and very fundamental function, which is the unit impulse function, which is also known as the direct delta function denoted by delta t, looked at its various properties and also the Fourier transform of delta t and delta t minus t naught, which is the shifted impulse or the shifted direct delta, alright. So let us stop here and continue with other aspects in the subsequent modules. Thank you.